Next talk is Don Hassler, Legacy of LASP Sounding Rocket Training.
Close enough. Okay, great. So my name is Don Hassler. I was at LASP between about 1985 and 1990. And I think one of the strengths of LASP, clearly under the leadership of Charlie Barth and the current leadership as well, is the strong association with the university, with the graduate students and the undergraduates. And part of that is a sounding rocket training program, because really it's the sounding rocket program is kind of like a microcosm of the larger space missions. You have every element of it. You write a proposal, you build the hardware, you calibrate it, you test it, you fly it, and you analyze the data. Except the beauty of a sounding rocket is you get to do it all yourself in each element of it in time sequentially. So sounding rockets are a great training ground, and I started off initially thinking I was going to do some statistics of the people that have come through LASP and had sounding rocket training here, or maybe just scientists that are notable in the field that have come through LASP, and that's pretty much everyone in the room and half the people in the field in general. So I thought I'd just focus on one element of the solar ultraviolet spectroscopy, which is what I focused on as a graduate student. There's three things you do with a sounding rocket program. One is you train the next generation of students, or next generation of scientists, whether they be undergrads or grads. You test and validate new technology, which is a key element of it, and there's been a lot of that done here. And you also do unique science, and that gets harder and harder to do in a 5-minute sounding rocket flight, but there's ways to do that. So I did my thesis actually with Gary on his EUV solar spectrograph payload, and this is a picture of Gary with the payload in 1987. I flew 3 rockets with Gary during that time. This is actually a paper that stimulated the payload that we then flew. This was this measurement of outflow in solar coronal holes. And this is actually one of the papers that really motivated the Soho mission, which came maybe 10 years later. But this saw basically outflows in a coronal hole in magnesium 10 line. It was a very important paper, and trying to quantify that and have a better understanding of that was one of the key elements of the following flights. Let's see, the first flight that I did as a graduate student was we were trying to measure the downflows or upflows, basically the velocities of coronal emission lines, as a function of across the limb. So we looked at one ray. In this sense, we looked at a very quiet region right at the equator, and you could measure the downflow, you could characterize it and measure it very precisely. One of the unique things about this flight, though, is we did some new technology. We actually flew a calibration lamp on the flight. This has been done for stellar astronomy, but it hasn't really been done for solar physics, and it hasn't actually been done since then. But we devised a way to put a platinum calibration lamp on the rocket, and intermittently takes data from the lamp and from the sun. So we got very precise measurements of the solar velocities along this line throughout the flight. And we also did some of the pioneering of solar imaging with multi-layer mirrors. Since then, there's the SDO mission, which is producing 4K by 4K images every second or every 10 seconds. Pretty significant, but these were one of the first ones that we flew on a rocket in 1988. So this was doing the first spectroscopy, measuring the first types of flow velocities in the corona during the rocket era of the 70s and 80s. Since then, once you start flying rockets, you kind of get hooked. Let's see, I've flown 10 now, I guess, and Tom Woods is down in the field. That's why he's not here, and I'm sure he's got twice that many. But I have a rocket program called RAISE, the Rapid Acquisition Imaging Spectrograph, and for this program we're trying to take basically 200 millisecond cadence images over either a small region of the sun to look at the high time cadence observations, and in this case you actually can benefit from the 5-minute rocket flight, because you can get about 3,000, between 500 and 3,000 images during that time. We're also doing some new technology with new types of detectors, as well as some new data acquisition systems. So it's not so different in terms of the optics in the ultraviolet. You have very simple optics. You can't have too many reflections, but we try to maximize. We had 2 detectors in this payload, so that we could get 4 different spectral band passes. We had a launch back in November of last year, And we have some very successful data. These are some images from a slit jaw camera, superposed slit jaw camera images on the left, superposed on an SDO image on the right. And basically, this is a chromospheric image, about 1,600 angstroms, looking at the chromospheric height in the solar atmosphere, looking for high time cadence changes. So this image right here is one Dopplergram taken of a wide scan in the wing of lymanalpha with intensity on the left and Doppler shift on the right, which is velocity, either upflow or downflow. And this is just one example of the types of observations that we do. This was taking the single one-dimensional spectroscopy that we did with Gary's flights back in the 80s, with now making it two-dimensional and trying to increase the time cadence. The next evolution, the sun is very complex, as you can see in some of those images on the right, and the different energies or different temperatures on the sun. But basically, fundamentally, you want to be able to do mapping of these velocities. You want to treat these spectral images sort of like magnetograms. If you look at a magnetogram, it's a very simple image that you can determine the magnetic, you can visualize the magnetic field. So the idea is to take a velocity map and be able to visualize the upflows, the downflows, or even the temperatures from those. These are some data now taken from Soho. This was the mission that was motivated by Gary's initial flights, and we see some very strong mapping of the outflows in the polar coronal holes on the right, which is the blue images on the upper right-hand corner. These are just some more images from that same mission, but all of this was motivated by those original measurements taken in the early 80s with Gary's early rockets. So as you look at these spectral data cubes, you basically look at velocity grams, you look at intensity images, you look at line width. You can piece all these plasma characteristics together to give you a very detailed understanding of the conditions on the surface of the sun. And the next evolution of this is to compare these remote sensed observations from spectrographs, the next generation of spectrographs, with the in situ measurements that we get as we send probes in close to the sun. So there's a mission now called Solar Orbiter, which is going to go into about 30 solar radii. There's another mission called Solar Probe, which is going to go into about 10 solar radii. And between these two in situ instruments also have the next generation of ultraviolet scanning imaging spectrograph on them, which will then be able to make measurements of the same emission lines that we would measure with the spectrograph, can also be measured with the composition instruments in situ on the spacecraft itself. So we can actually, with modeling, trace the plasma flows from the surface, the conditions we measure at the surface with our spectrograph, and trace it all the way out to the satellite and measure and compare those with the in situ measurements on the spacecraft itself. So basically, in the last 35 years, ultraviolet spectroscopy of the sun has evolved in much the same way that we get major advancements every time we send a new mission to a new planetary system or to a new location. Or enable a new technology. But all of this is rooted in the training that starts here at LASP and continues on here at LASP with the scientists and the researchers and the graduate students and the postdocs that either stay here or come back here or go elsewhere. But LASP as a nurturing source of really the training for the future generation of scientists is really the point of this talk. Thank you very much.
Questions? Oh, it's Rockies. Come on, some of the best parts.
Yeah, on your rays picture,
Yeah.
you had some what looked like linear features going horizontally across that. Were those real?
Here?
No, next one. There.
Well, I'm not sure this has been flat fielded, so that could be a flat field effect. The line going across is the actual, there's the slit jaw image. You can actually see the slit locate on it.
I'm looking at what look like dark features that go.
This way.
Yes.
That's flat field. This is the entrance slit.
Okay.
Anything else? Thanks, Don.
Great, thanks.